So we're going to try and do inorganic. Most of it is mainly memorization. I just these are just very concise, brief notes, but they need some explanation as well. Uh, Now period three is in your course, and we're going to do and cover period three. Period three is sodium, magnesium, aluminium, and then there is silicon, then phosphorus, sulfur, chlorine, and argon. That's your that's your period three, all of it. The first thing is the melting points. Okay, we're going to talk about the melting points. Remember the melting point. I mean, this is kind of incorrect. The melting point of sodium is actually even lesser compared to sulfur, somewhere over here. So sodium is relative in relative terms. Sodium's melting point is not very high. Okay, not this one. So I've removed that. Okay, corrected the graph. Uh, Now we're going to talk about the first three. Uh, they have metallic bonds and they usually have high melting points. So we're going to talk about melting metallic bonds because they're going to talk or ask questions about this and comment on the trends in the melting points. So the question is, what is metallic bonding? Metallic bonding is that you have positive metal ions in a sea of free moving electrons. So there would be lots of
Where's the volume?
so there would be lots of positive metal ions in a sea of free moving electrons. So that is metallic bonding. And if you're being asked to describe this, this is all O-level stuff. This is known as a giant metallic lattice. Okay, let me get rid of this for a second. So this is known as a giant metallic lattice because all metals like to lose electrons. So it's a regular arrangement of positive metal ions in a sea of free moving or delocalized or mobile electrons. Okay, that's metallic bonding. So the question now is, one question that can be asked about this is that why is there variation in the metallic bonds of NaMg and Al? Why is Na uh, uh, has a lower melting point and Mg has a higher melting point and aluminium has an even higher melting point? So why is there variation? So this is, let's assume this is Na. Now the reason is Na is group 1 and it loses one electron, forms a plus 1 ion, which is why metallic bonds in Na are weaker. When you move to Mg, the thing that would change is that the metal ions, the size would also decrease. Plus, there's going to be plus 2 charge. There's going to be plus 2 charge, and there would be more delocalized electrons. So each Mg is going to have, it's going to produce a lot more delocalized. It's going to produce a lot more delocalized electrons. And then you move to aluminium. Now, what's going to happen with aluminium is that the size of the aluminium ion is going to be even smaller. The size would be smaller, plus the ions are going to have a charge of plus 3, each one of them. Aluminium likes to lose 3 electrons. There are 3 electrons in its outer shell, It ends up losing 3 electrons. So the number of delocalized electrons is going to be a lot more compared to the other two. So I'm going to make,
Sir,
yes.
uh, magnesium has a charge of +2, aluminum has a charge of +3, and there is not much of a difference between their melting points. Why is there a greater melting point between
हाँ वो
sodium
भी
and magnesium then?
नहीं वो भी क्वेश्चन आता है ठीक है I mean they've actually asked that ठीक है अच्छा first thing why is the melting point increasing ठीक है I'll come to that because as you can obviously see it's not a gradual trend it's like Na is like abruptly lesser, Mg is far greater, and then aluminium and Mg are kind of similar to each other. Acha, so what happens when you move from Na, Mg, and Al? Why is the metallic bonding increasing? Why is the strength increasing? The reason it's increasing is that the ionic radius decreases. That's one. Charge increases on the metal ion. Acha, why is the ionic radius? Why is the ionic radius decreasing? The reason is that they have more protons. They're all isoelectronic. Na, Mg, and Al, they have exactly the same number of electrons in the ion form. Na is +1, that is 10 electrons. Mg is +2, that's also 10 electrons. Aluminium is +3, that is also 10 electrons. They have exactly the same electronic configuration when they are ions. That means they are isoelectronic. But aluminium has far greater protons. It has 13 protons. So the electrons, the same number of electrons are attracted a lot stronger in aluminium. Na only has 11 protons. So the size of the atom is kind of slightly bigger. ये end में they would be written over here. I mean this thing over here. As you move to the right, you have more and more protons, and because of more protons, there's more attraction for electrons, and the size, although the shells are the same, but the size of the ion and the size of the atom is going to be lesser. So if the ionic radius is decreasing and the charge increases, that indicates that the charge density is increasing. The charge density increases. And then there's another point, which is that they have more delocalized electrons. Down this thing, NaMg2Al, you have more delocalized. Nee, I'm going to come to that. Okay, just a second. I said they also have more delocalized electrons. So, which is why the metallic bonds are stronger. The metallic bonds are stronger because of all these factors. Okay, all these factors they lead to the fact that stronger metallic bonds are going to be formed. Because at the end of the day, it's the delocalized electrons that are attracting the positive ions. So, and the positive ions attracting the electrons back. So they're going to have stronger metallic bonds when you move down the group. Now the question is, why is there a significant jump when you move from Na to Mg? There's a large increase in melting point when you move from Na to Mg, but that's not happening when you're moving from. One second, let me move this. I think it's here. So the question is, why is there a large increase when you move from Na to Mg? But there isn't a large increase when you move from Mg to Al. Okay, so there's a large increase in melting point, and Mg to Al there is a small increase. So the answer to that is very simple. When you move from Na to Mg, Madhuta, by what percentage does the charge increase? Can anyone tell me? Na is +1, Mg is +2.
Double.
By 1%.
Well, by 100%, right? I mean, the increase is 100%.
G.
Okay, so there's a 100% increase in charge, but it's basically doubling, right? And also the number of delocalized electrons and the number of mobile electrons, right? So when you move from Na to Mg, all of a sudden everything doubles. Na is +1, Mg is +2. That's twice the charge. Na has one delocalized electron, like but Mg produces double that. It produces two electrons. So which is why there's this significant jump. Na and Mg are going to have, like, there's going to be a large variation in the melting points. But that jump doesn't occur when you move from Mg to Al. Now, when you move from Mg to Al, there is a small increase in melting point, a relatively small increase in melting point compared to the above. अच्छा उसका क्या difference है? Now what happens? At Mg the charge is +2. For Al the charge is +3. So by what percentage is the charge increasing?
50.
ठीक है, that's just 50% increase. ठीक है, so 50% increase in charge as well as the number of delocalized electrons. Like Mg lost 2 electrons, Al loses 3 electrons. So that's an increase of 50%. And the number of mobile electrons. So, which is why the jump is less significant between Mg and Al, and it's way more significant between Na and Mg. Okay, the strength in metallic bonds almost doubles when you move from Na to Mg. There's a 100% increase. But when you move from Mg to Al, the difference is, in relative terms, the difference is not that much. It's only a 50% increase now. Okay, is this clear, Bazar? Is this clear? Does this answer your question?
Yes, sir.
Okay, is this clear to everyone else? Ethan, Mohammed, Rida, Hiba, is this clear?
Yes, sir.
Okay, and you've actually been asked about this. Okay, it's a past there's a past paper question specifically on this. So just remember this. I mean, they obviously have metallic bonds, but you have to go into the detail as well. Acha, what about silicon? It has a macromolecular structure. You need to know, uh, which is why silicon has a very high melting point. You can see over here. Silicon has a silicon has a macromolecular structure. So let's talk about silicon and let's discuss its structure. So silicon is as a silicon. It's a giant covalent macromolecular structure, and it's exactly like diamond. Similar to diamond. Uh, so every property is almost the same, except that silicon is a big atom. Big atoms, they don't form that strong bonds. I mean, it is a strong structure, but not as strong as carbon. Carbon is a small atom. Small atoms, they form much stronger bonds. And so, what would be the structure like? You might be asked to draw this, like in the rough way. So, silicon would be tetrahedral. Each silicon atom would be making each silicon atom would be making 4 bonds, and then further, each silicon atom would again be making 4 bonds, and the whole thing just continues. It's one tetrahedral structure on top of the other, and the bonding would just continue in all directions. So there are going to be lots and lots of bond. Uh, So you might be asked to draw this. The bond angles are going to be 109.5, and it's a tetrahedral. It's a tetrahedral structure. Uh, it's strong and it has high melting points. Why does it have high melting points? Because uh, to melt, you need to break large number of covalent bonds. So you need to break a large number of covalent bonds. So which is why they have high melting points. Okay, so hopefully this is clear to everyone. Then you're going to talk about these phosphorus, sulfur, chlorine, and argon. You have these four substances, and all of them are simple molecular. Now, when they are simple molecular, they have intermolecular forces. And so let me discuss these. Where do I discuss this? One second. Let me discuss it over here. Okay, on the extreme. So let's talk about P4, and after P there is S8, then there is Cl2, and then there is argon. Now all of them are going to be non-polar. Okay, so they are non-polar molecules. Why non-polar? Because there's not going to be any electronegativity difference. Like in a sulfur molecule, all atoms are sulfur, so the electrons would be evenly shared between the atoms. So they're non-polar and simple molecular. So they form simple covalent molecules. And uh, so let's say, for example, a Cl2 molecule. That means the molecules are free to move around, and they are kind of independent molecules. Then they don't have any connections with each other, except for these weak van der Waals forces. All of them are going to have weak van der Waals forces. Weak van der Waals, which are known as temporary or instantaneous dipole. So they would have fluctuating dipoles. Like for some odd reason during a collision, this side could become partial negative, the other side could become partial positive, and so on. And it would induce a dipole. The electrons over here are going to get repelled, and this side would become partial. I mean, they're not going to get repelled, they're actually going to get attracted because this side is positive. So the electrons will get attracted to this side. This side would become partial negative, this side would become partial positive, and there would be attraction, mutual attraction. So there's going to be temporary dipole and induced dipole. So if this is negative, it's going to repel the electrons in the other molecule. And this side would become negative, this side would become positive. So fluctuating dipoles would be created in the molecule. There would be random temporary dipoles, induced dipoles that would be forming, which would lead to attraction. So temporary dipole, induced dipole interaction. And all of the molecules are going to be similar. Now, van der Waals depends on one thing, and that is size. Bigger molecules have more electrons. So bigger molecules have more electrons, hence they are going to have more van der Waals forces. So they're going to have more van der Waals forces, and they're the ones that are going to have relatively higher melting points. So the one at the top would be that S8 is the biggest molecule. It's going to have the most van der Waals forces, and then you're going to have phosphorus, which is P4. Then Cl2 is smaller than both of them, and then you have argon. So the melting point or the boiling point or whatever, it they decrease. So melting and boiling points they decrease as size decreases. So that's one thing. P4, S8. So is this clear to everyone?
Yes, sir.
ठीक है मिनाहिल, is this clear?
Yes, sir.
Aiza? अच्छा.
Yes.
Yes, sir.
So now another thing about them is you must know the structures of these molecules. I mean, Cl2 is obvious. I'm going to talk about P4 structure. Uh, you must know what the structure of P4. What does P4 look like? So remember P4. Okay, let's talk a bit about P4. P4 has two forms. Okay, so it's also I think mentioned in the sheet somewhere, probably in the on the next page. One second, and I've lost the sheet. Okay, it's given over here. One second. Okay, well. Okay, just one second. Let the board load. So P4 is actually given over here. Okay, in the sheet. There is white phosphorus. White phosphorus is four phosphorus atoms all bonded to each other, and it has this pyramidal shape. Like every phosphorus is bonded to three atoms. Let me show you the actual three-dimensional. Hopefully, actually, this is what P4 looks like. TK, if you can see this properly, and if you can have a bigger image. Okay, so this is what phosphorus looks like. That every phosphorus is making three bonds. It's like a pyramid, and at the ends of the pyramid, the atoms attached. So that's how four phosphoruses are going to be bonded to each other. But then there is the polymeric form, which is called the red phosphorus, which is also mentioned over here. Now, in red phosphorus, what happens is that a polymer forms with P4. So let me draw the molecule of P4. I mean, the first one is going to look like this. That there's going to be, let's say, this is the base of the pyramid. And then there is one phosphorus sitting right at the top, which would be connected to all of them, right? So that's like a pyramid. Okay. Uh, Now the polymeric form is. Let me see if I can copy this. So the polymeric form is that lots of these phosphorus molecules they might line up, and under certain conditions, one of the bonds between the phosphorus atoms they're going to break, and some new bonds are going to be formed between them, which would connect the two structures together. That's your polymeric red phosphorus. Okay, this is what I've shown in the notes as well over here. Okay, this is what's happening over here as well. Is this clear? Abba, is this clear? Ethan, is this Mohammed? Is this clear?
Yes.
Yes.
Yes, sir.
So then about S8, although it's never been asked, which is why I've never actually, it's not even in your course. I mean, even this wasn't in your course, but there was a question on this. They actually, I mean, the question was, I mean, this is not in your course, it's not in the syllabus, but the question was they gave you this structure and they were asking you that there's another form of red phosphorus and that's a polymeric form. And they had actually asked you to draw the polymeric form. And although they, I think the examiner was actually thinking that people would be able to guess this polymeric form since they haven't studied. It's not in your book, but they gave this. So similarly, maybe I mean it would be much better if you know what the structure is. So let's look at the S8 molecule as well and its structure. Okay, I mean that's simple. Basically, it's 8 sulfur atoms all connected to each other. And remember, sulfur has an angle of 104.5, which is why you see this crown shaped structure. Because sulfur has two lone pairs. So if you have two lone pairs over here, the lone pairs are going to bend the bonds and keep them together at an angle of 104.5. It's not going to be a straight bond. So this is what an S8 molecule looks like. So we can, I think, I mean, I can try and draw this S8 molecule just to be on the safe side. You might be asked about the shape. I mean, you've actually been asked about P4, so maybe they might ask something about this structure. So sulfur is S8. So that's one, two, three. Uh, so I think it was. So this is five, and then you have. This is five. How many left? Three more. So maybe like this. I'm not actually able to draw this perfectly, but probably something like this. So just 1 minute break. Actually, let's continue. This is all about. Actually, remember, you must. I mean, you have to memorize all the reactions, but you have to remember the details as well. A lot of the details are fairly straightforward. Shouldn't be that difficult to remember. Okay, uh, and they're related to the rest of the chemistry. Okay, so remember this, all of this as well. Now let's move to the next part: electrical conductivity. I'm not going to comment much about this. It's already written over there. NaMg and Al are good conductors of conductors. Why? Because they're metals. And silicon, phosphorus, chlorine, and argon are pretty bad conductors of metals. Why? Because they're non-metals. Uh, we must know, why do metals conduct electricity? Anyone?
Because they are free moving electrons.
Okay, so obviously, I mean, you must know that. Okay, so that's fairly obvious. You are free and mobile moving electrons, right? And which one do you think is the better conductor, NaMg or Al? Like according to the structure,
Ammonium.
okay, so it's going to be aluminium. So I think that's obvious as well. And why that aluminium has way more delocalized electrons. So that must be. I mean, there's no space to write that, but that's fairly obvious. Which is why you use aluminium as wires, and you use it for high voltage transmission. It doesn't rust as well. Okay, we're going to talk about. I mean, it must be written somewhere that aluminium doesn't rust, and it's used in high voltage transmission because it's a very good conductor of electricity. Then we talk about the reactions with water. The first one, uh, all of the substances reacting with water. So Na, it reacts very vigorous. It almost has an explosive reaction with water, and a strong alkali is formed. And you get what would you see? H2 gas is being formed. So you're going to see bubbles forming. I mean, don't write bubbles, write effervescence. And sodium floats and fizzes on the surface. It's a low density metal. So it floats and fizzes on the surface, doesn't sink. Uh, then Mg with water, the reaction with Mg with water is not an easy reaction, especially at room temperature. MgOH2 and hydrogen gas are produced, but it usually requires very, very high temperatures. Aluminium absolutely has no reaction. Why? Because it has a non-porous unreactive Al2O3 coating, which you've studied in O levels, and this was a very common question that you got in O levels. That there's this tough, non-porous, and unreactive coating of Al2O3. The rest silicon is this giant covalent structure, so it's obviously not going to react. About Cl2 reacts with water to form HOCl and HCl. It hydrolyzes. So remember that. Oxidation states, some of the common oxidation states are that, I mean, Na, Mg, and Al are fixed, almost fixed oxidation states. Silicon is +4, phosphorus, and silicon is mostly +4. And remember, silicon forms covalent compounds, not ionic. Remember, oxidation states is not the charge on the substance. How do you? I mean, a lot of people get confused with this, but remember, silicon, phosphorus, or sulfur, they don't actually have +3 or +5 charges. What we're talking about when we talk about oxidation states is that if phosphorus is bonded to Cl, then Cl is more electronegative. So the electrons are closer to Cl or slightly closer to Cl. So when we talk about oxidation states, it's a covalent compound. Phosphorus doesn't really have +3 charge. What we just assume is that since Cl is more electronegative and Cl is partially or very slightly pulling the electrons more strongly towards itself, so we just assume or treat this molecule as an ionic compound. That what would happen if this was an ionic compound? Because when we talk about redox reaction, we just want to know who's gaining electrons and who's losing electrons. We're not really concerned whether they're gaining electrons just very slightly or whether they're gaining electrons completely. Even in ionic compounds, the electrons are never gained completely. Like in NaCl, Cl is -1, and Na is +1, and it loses electrons. But it's not, it all depends on the electronegativity difference. It's not going to be a complete 100% loss of electron. A lot of times it's not a 100% gain of electrons or a loss of electrons. So when we talk about redox reactions, we basically look where the electrons are. Are they closer to Cl or are they closer to phosphorus? So we just treat it as if it's ionic, as if phosphorus has lost all these electrons, and we give it a +3 charge. So that is oxidation states. And remember the common oxidation states of phosphorus, of sulfur, which is +4 and +6. SO2 could be formed, and SO3 could be formed as well. Then over here, it's the reaction of the oxides with water. The first one, nothing happens; it simply dissolves, and NaOH is formed. The second one, a weak alkali is formed. Why does a weak alkali form? Because MgO is not very soluble. If you know the solubility table, then MgO is not very. So MgO is not very soluble. And then you have aluminium oxide. Uh, that obviously has no reaction. Silicon, this is sand, no reaction. Remember this phosphorus oxide. Phosphorus has two oxides. It has an oxide with a +5 oxidation state. This one is the one with +5. It forms an acid where it's going to be +5. Phosphoric acid, phosphorus is going to be +5. Then it has another oxide which is +3. So the acid would also have an oxidation state. The phosphorus in the acid would also have the oxidation state of +3. Uh, And these two oxides are also sometimes written as P2O5, and this one is sometimes referred to as P2O3. Okay, so remember these two oxides, and then you have SO3 and SO2. They form sulfuric acid and sulfurous acid. And again, this is +6. So +6 sulfur would produce an acid which has sulfur in the +6 oxidation state. A +4 sulfur would produce an acid where the sulfur would be in +4 oxidation state. So remember this, SO3 would produce as H2SO4 and SO2 would produce H2SO3. So you have to remember all of this, the reaction of the oxides with water. Okay. So is this clear? I'm going to continue with this in the next class then. Okay. ये यहाँ पे छोड़ दें because the next thing is requires a lot more explanation. The reaction of chlorides with water.
चलिए ओके सर अल्लाह हाफिज
ये मैं भेज दूँ. I'll send the worksheet. I'll send these notes. I have already sent them, but I'm going to send them again. ठीक है. Okay then.
Yes, sir. Allah.
ओके सर अल्लाह हाफिज
Yes, thank you.
Thank you.